you got a 3 here, so it's asking you to take the third choice in the third. You look at transition rule and may only have two choices, but it's asking you to take the third one. Well, that makes that an invalid address. Now, since you're systematically going up one by one all possible addresses, starting from a very small number and breadth first, you're building up. A lot of these addresses will be invalid, right? Because if you have n layers in your tree, the number of possible addresses is going to be h to the power n, right? Is that right? Well, more than that, in fact. So most of them will be invalid. Okay, so when it is invalid, just skip to stage 4. Another way to go to stage 4 is if you come across a reject configuration. Okay, skip to stage 4. Now, if you come across an accepting configuration, you find your next node and you look at it because it's known from your n. That's presumed known already. So if you get to a particular node that has an accepting state in it, it's an accepting configuration, then you accept the input. All right. Okay. Now, what is stage 4? Well, basically, it's just updating your address. So stage 4. Just replace the string in type B with the lexicographically next string. In other words, just if you're talking numbers, let's say, you just increment the address by 1. Right? That's all it is. You're just systematically counting up through all possible addresses, and you're starting with low numbers and you're systematically going through them. Like let's say little b was 2. Okay, so we're now talking the binary numbers. Okay, so all possible addresses would be 0, 1, and then 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, and so on. Okay, so that's effectively what you're doing with this. You're systematically incrementing the address. Now, probably the majority of those addresses will be invalid. They're predicting a particular node that does not exist in the tree, because you can have of the order little b to the n of that order possible addresses, but they aren't anywhere near that a number of nodes in the tree. Okay? So most of the addresses will be invalid. They're referring to nodes that don't exist. Okay? All right. So that's all that stage 4 does. It just effectively increments the address systematically. Okay? And most loops, as you're using the address, will be invalid. So you just skip back to stage 4 and increment again and again and again and again. Right. So if it is valid, you increment the address and it is valid, we'll then go back to stage 2. Okay? And then, okay. Well, that's effectively the end of the proof. Now, obviously have not done it in detail, because that's too tedious with Turing machines. So as usual, it's a fairly high-level proof, but you can see, I hope, how it's done. Right. But there's a corollary to it, corollary 3.18, and here it is. I talked about this earlier session. So here's the corollary statement. Corollary is just an after theorem, usually fairly simple, quickly deduced from the major theorem that preceded it. Okay? So a language is Turing recognizable if and only if some non-deterministic Turing machine recognizes it. Now that's pretty similar to what we had. Now what's in the previous corollary? What's different? That's the P's the same, isn't it? Let me just check. A language is Turing recognizable. A language is Turing recognizable. Yeah, so the two P's are the same in both corollaries. And what's different? Some multi-tape TM recognizer, that was in the previous one, and here we've got some non-deterministic recognizer. Okay, so the only difference is this term here. Makes sense. Alright, well again, the same critique. I won't bother reading out Sipser's proof, but it was it suffered from the same faults as the previous one. So you know, I do the pure math type approach. So again, as usual, I do the if case first. In other words, P if Q. This first part, label that mathematical statement, call it P. And the second mathematical statement, you know, the other side, the right hand side, the right hand side of the IFF, if and only if, call that Q. Okay. So the if case, P if Q. In other words, if Q then P. You know, Q arrow P. So we start with the right hand side and deduce the left hand side. Start with Q, deduce P. Alright, what does Q say? There is some non-deterministic, there is some N, right? It says there is an NTM, non-deterministic Turing machine, that recognizes the language. Okay? And therefore, since, because an NTM has an equivalent DTM, we just proved that. That was theorem 0.316. Okay, for any this theorem, it says that for any non-deterministic Turing machine, you can construct an equivalent, you know, same power, does the same job, DTM, deterministic Turing machine. Okay, so there is a deterministic machine that recognizes that language. Okay, therefore the language is Turing recognizable by definition. Because what does Turing recognizable mean? It means there's a deterministic Turing machine that recognizes it. Right? So that's the if part done. And the only if, the other way, P only if Q, in arrow terms, that, you know, if P then Q. In other words, from left hand side, you start with the left hand side and prove the right hand side. So you know you start with P. And what does P say? P says, you know, there is a language that is Turing recognizable. A language is Turing recognizable. Okay. Now, what does Turing recognizable mean? Well, that just means that there's a deterministic machine that recognizes it. Right? Therefore, there is a deterministic machine that recognizes it. Right? But there's a non-deterministic machine that's equivalent to that deterministic machine. You know, we just proved that in the previous theorem, right? Theorem 3.16. Therefore, that non-deterministic machine recognizes the language. End of proof. End of proof sign. Now a bit of a comment at the end. Now you can modify the above proof so that if N always halts on all branches of its computation, then D will always halt. Now it's a sort of a variation, if you like. So you can change your proof somewhat so that if your N does, you know, always halts, so you don't have these infinite branches, right? You could change your strategy. Perhaps you could try then depth first. I don't know. Anyway, okay. So that if any branch the N TM takes, it will halt, right? No matter. So it doesn't. So it does not. It's not the case that there is a branch that goes on infinitely, right? There are no such branches. Okay, and for such an N, you can find a D that will always halt. Okay. Now, an NTM like that is called a decider. The NTM is called a decider, right? If all branches halt on all inputs, okay. And then you said in the exercise section, the end of the chapter, the problem session, exercise 3.3, you're asked to modify the proof this way, you know, to do this, and that the result of that that leads to the following corollary, another corollary, but run out of board, run out of session, so won't be able to. So we'll just follow that first thing next session. Okay. So the essence of it. So if underline it twice. If your non-deterministic machine halts on all branches, doesn't go down infinitely, then you can find an equivalent deterministic machine that also halts on. It'll always halt. It'll always halt. And such an NTM is called a decider. That's sort of the essence of it. Okay, ciao.